Good morning. Now this is class 2. Now here we will discuss about ideal junction properties and current voltage relationship. In the last class we have discussed about Schottky junction and some qualitative characteristics. Now what about ideal junction properties? Now the electric field in the space charge region or depletion region is determined from Poisson's equation. So we have the electric field as with respect to x, dE by dx will be equal to rho x Es, epsilon s. Here rho x is the space charge volume density and epsilon s is the permittivity of semiconductor. Now suppose that the semiconductor doping is uniform. Then on integrating equation 1, naturally on integrating dE by dx we will get E as equal to E na ndx by epsilon s plus c1. So it's better you write on integrating, assuming that the doping is uniform, then by integrating equation 1 you get the expression for E as this one, okay, plus c1 is a constant of integration. Now our next aim is to find the value of c. Okay, for that we assume that electric field is 0 at the space charge region in the semiconductor. So you get the value of C1 as minus E N D Xn by epsilon s. Here Nd is the doping concentration or donor atom concentration. Now substitute the value of C1 in equation 2. So that equation 2 will get modified as E is equal to minus E Nd by epsilon s within brackets xn minus x. Now this is a linear function of distance only in the case of uniformly doped semiconductor, because we have assumed that the semiconductor doping is uniform and it will have a maximum value at metal semiconductor interface. Since electric field is 0 inside the metal, a negative surface charge will exist in the metal at the metal semiconductor junction. Now our next aim is to find the expression for space charge width or depletion region width. So for that the result that we obtain in the case, that is the width of depletion region for a uniformly doped semiconductor is given by W is equal to 2 epsilon s within brackets VBI plus VR. VBI and VR already we have explained in the last class, by E Nd the whole raised to half. VR is the magnitude of the applied reverse bias voltage. Now a junction capacitance can also be determined, and that expression for junction capacitance C dash is given by root of E epsilon s Nd by 2 VBI plus VR, that is equation 6, that is capacitance per unit area C dash. Now we are going to square the reciprocal of equation 6, then what we get is 1 by C dash square will be equal to 2 VBI plus VR by E epsilon s Nd. That is symbol that we can get from equation 6. So let that be numbered as equation 7. Now this equation 7 can be used to obtain the built-in potential barrier, that is VBI, and the slope of curve from equation 7 will give you the doping concentration or semiconductor doping Nd. So that is how you calculate the value of built-in potential barrier and the value of semiconductor doping Nd. Also we can calculate the potential phi n, and from that we can also calculate Schottky barrier, that is phi b0, from the equation VBI equal to phi b0 minus phi n. That is, once you get VBI and phi n, definitely you will be able to calculate the Schottky barrier, which is phi b0. So this is how you determine the values of built-in potential barrier, then semiconductor doping, and finally Schottky barrier. These are the steps involved in determining these three parameters. So these three slides deals about how you determine the values of these three parameters. Now next session is current voltage relationship. The current transport in a metal semiconductor junction, it is mainly due to majority carriers. Now especially in a rectifying contact with n-type semiconductor, that current transport mechanism is that of electrons over the potential barrier, which is mainly explained by thermionic emission theory. Now, to derive that thermionic emission characteristics, we assume that barrier height is larger than kT. So, we use the approximation Maxwell-Boltzmann approximation for that purpose. Now, the figure shows one-dimensional barrier with an applied forward bias voltage VA and two electron current density components. Here, the current, that is JSM, that is actually the current density due to flow of electrons from semiconductor to metal, that is S to M, semiconductor to metal. Then naturally what will be Jm to S? It will be the flow of electrons from metal to semiconductor, just the reverse. Now the current flow or the current density from semiconductor to metal, that is J from S to M, is a function of concentration of electrons, and it is given by E, charge of electron, integral of EC to infinity Vx dn. Here EC dash is the minimum energy required for thermionic emission into the metal, whereas Vx is the carrier velocity in the direction of transport. E is the magnitude of electronic charge. So all these terms they have explained. That is the terms for determining the current density from semiconductor in metal. What is E, what is Vx, and what is EC dash. Everything is written here. Now the increment in electron concentration, that is, let n be the concentration of electrons, then the increase or the increment in electron concentration dn is given by Gc of E, that is nothing but density of states in conduction band, FFE, it is the Fermi-Dirac probability distribution function, then dE. Now as already said, we are using Maxwell-Boltzmann approximation, so we get the expression for dn as this. This expression we have already studied in solid state physics. When you refer any book, you can see this equation. Now, if all energy, electron energy above EC, that is conduction band edge, is assumed to be kinetic energy, then half Mn V square will be E minus EC. EC is the conduction band edge. Okay. Now, the net or the total current density in the metal to semiconductor junction can be written as J is equal to J S to M minus J M to S, and it is defined to be positive in the direction from metal to semiconductor. Now we get the expression for the net current density capital J as given by equation 1. Here A star is given by this expression, and it is called effective Richardson constant for thermionic emission. Okay, so this is actually the derivation for this constant. Now, in the above case, equation 1 can also be written in the diode form. You know the diode form, which is similar to that diode form. Equation 1 is rewritten as this. Here, JST is the reverse saturation current density and is given separately as this equation. Now, in terms of this barrier, Schottky barrier height, JST can also be written as this. And now the change in barrier height, that is phi b, delta phi, will increase with increase in electric field or with an increase in applied reverse voltage. So there are many possibilities of asking this question. Let's show that the change in barrier height increases with increase in electric field. So that means you have to derive up to this equation, or sometimes they will be asked to derive the expression for this Richardson constant. Then also you can write this essay. Now this figure shows the reverse bias current voltage characteristics of a Schottky barrier diode. From here you can see that reverse bias current increases with the reverse bias voltage. Why? Because barrier lowers. Now the last slide is, we note that the reverse saturation current density of tungsten silicon and tungsten gallium arsenide diodes in figure, that is what is shown here. It differ this figure. differ by 2 or orders of magnitude, and that is seen in the effective Richardson constant, where it is assumed that barrier height in the two diodes, that is in tungsten silicon diode and tungsten gallium arsenide, they are actually A star is the same. So the definition for Richardson constant contains electron effective mass, and that electron effective mass is different for these two diodes, and the fact that effective mass is an expression for A star or Richardson constant is a direct result of using the effective density state wave functions in the thermionic emission theory. So the net result is that Richardson constant A star and JST will be different, or they vary between silicon and gallium arsenide. This slide you can skip, this is just an example. Okay, no need of studying this slide. If you want, you can write this, draw this graph, but up to this much is very important. That is, most probably you will be asked to discuss about the current voltage relationship, or derive the expression for Richardson constant, or anything like that. So you can write this slide, and all these slides you can write up to this much. Okay. Or sometimes the question will be, as already said, show that the change in barrier height increases with increase in electric field or with the increase in applied reverse voltage. So up to this much you can write. If you want, you can mention this one you can skip, no need of writing. Okay, so study that. Thank you.